So you get n minus 1 edges. Now look at this vertex A1. By definition, the way this is constructed, it is not equal to, all the A's are different. A1 is not equal to B1, B2 up to Bn minus 2. Okay? What that means is the degree of A1, so let T be the constructed graph. So you have a you have a graph in which you have n minus 1 edges. Yesterday we proved that if you have n minus 1 edges and there is no cycle, then it must be a tree. This is something that we proved yesterday. So that is what I want to use. Look at this. There cannot be a cycle that contains A1, impossible. Why is that? Because the degree of A1 in T is equal to 1. A1 has degree equal to 1. How can there be a cycle that contains A1? Its degree will have to be at least 2. If there is no cycle that contains A1, then there cannot be a cycle which uses the edge A1, B1. Since A's are different, degree, no cycle. Next, look at A2. How can I really have a cycle that contains A2? A2, the way it is constructed, it is not equal to B2, it is not equal to B3, B4, any one of those B's. It is also not equal to A3, A4 up to An minus 1, An. Therefore, the only way you could have a cycle that contains A2, it will have to use this previous edge A1, B1, but we already said that there is no cycle. If must use a contradiction. So no cycle. You can now just continue in this manner. That's exactly. You can inductively assume that there is no cycle up to A1, B1, A2, B2, A3, B3 up to AJ, BJ. Argue that they're using AJ plus 1, you could not have a cycle. Because such a cycle, AJ plus 1 would have to be equal to some BI previously, but there is no cycle that uses the previous AJs, etc., etc. Continuing in this manner. This is one way, of course. You could alternatively also prove that your graph, this will be connected graph, that it will be a connected graph. So T is a tree. A good fallout of the proof for correspondence, consequence of proof for correspondence is, you see that in the proof for correspondence, number of times is equal to degree of j minus 1. Degree of that vertex j. So if your vertex j has degree equal to 1, that is its leaf, it will not occur at all in the proof or code. If its degree is equal to 2, then in the code it occurs once. If its degree is 10, then in the sequence it occurs 9 times, etc., etc. One less. Okay? So this is sum of all the degrees. We have n minus 1 edges, therefore the sum of degrees should be equal to 2n minus 2. 2 times n minus 1, that is equal to 2n minus 2. Then the number of label trees in which degree of I is equal to di is given by n minus 2 factorial How does this follow? Because proof all sequences j occurs dj minus 1 times. If degree of j is dj, then it occurs dj minus 1 times. This is now a question on what is called multinomial coefficient. It is actually a multinomial coefficient. You have as many as n minus 2 things there. Yeah. D of j minus 1, this is okay. Yeah, no, let's see. Yeah, which thing has not occurred in the proof or code? Yeah, yeah. N can occur in the proof or code. It's good you asked that question. N can very much occur in the proof or code. I think you're just confused there. 9, for example, could occur in the proof or code. Is that clear? What you are saying is 9 will not become a smallest leaf is what you are saying. But what we are writing there, it's good you asked that question. We are not writing label of leaf. That is not what we are doing. We are writing label of the vertex which is adjacent to that leaf. Is it clear? So 9 can very much occur in the proof or code. There's absolutely no problem at all. I mean, I could really have a proof or code in which all entries are equal to 9. would this look like? I mean, it actually is, this is clear. That's a star, okay? I would be writing 9 8 times, in fact, that's, no, 7 times, okay, not 8 times, 7 times. Is that clear? Because what we write in the Prüfer code is not the label of the leaf. It is not at all the label of the leaf that we write. Leaf is thrown out. What you write is the label of the vertex adjacent to the leaf. Okay? Therefore, it's perfectly all right. Any other question? Now, this is a very carefully carved out procedure. It's a very, very carefully worked out procedure. Anything, in fact, absolutely anything can occur any number of times. There's no problem at all. I could write anything any number of times or not write at all. That's why these sequences are free. The length is fixed. Length is n minus 2. And the numbers take values from 1, 2, 3 up to n. But any. So we have to choose dj minus 1 of the b's to be j. You see, it's like this. There are n minus 2 slots available with me. There are n minus 2 slots available with me. Some of them I want to write j there. How many places would I be writing j? That is exactly dj minus 1 times. How many places would I be writing 1? d1 minus 1 times. How many places would I be writing 2? d2 minus 1 times, etc. So this is like n minus 2 things are available, n minus 2 slots are available to me. At some of those slots I write 1, some of those I write 2, some of those I write 3, etc. So this equals, this is what is called a multinomial coefficient. More general than the binomial coefficient. What is this equal to? The standard definition? It is n minus 2 factorial divided by d1 minus 1 factorial, d2 minus 1 factorial, etc. up to dn minus 1 factorial. That's exactly what you have there. Okay? This has quite nice consequences. One of the consequences, for example, is I want to find out, I know that there are n raised to n minus 2 label trees. I have as many as n raised to n minus 2 total number of trees. Out of these, how many fix a j? How many would have j as a leaf? If j is a leaf, then j does not occur in the Prüfer code at all. J does not find a place in the Prüfer code. Anything that is a leaf is not to be found in the Prüfer code. That means the Prüfer code that you construct is actually on the remaining n minus 1 numbers. Okay? So the number of with j missing there are n minus 1 possibilities now. 1, 2, 3 up to j minus 1, j plus 1 up to n, but there are n minus 2 places. N minus 2 places still to be filled. Okay? So it is n minus 1 raised to n minus 2. Out of Equivalently, if one uses the language of probability, the probability that a randomly chosen tree will have j as a leaf is given by taking the ratio of these. So the probability that j will become a leaf, there are as many as in the other room, there are n raised to n minus 2 trees. Somebody has drawn all the n raised to n minus 2 trees. Blindly, I put my hand on some tree and ask the question, is j a leaf or is not a leaf? There are only two parts. The probability that j will become a leaf is this number divided by that number. Is that clear? So, yes, is there a question? Is it? So the is n minus 1 raised to n minus 2 divided by n raised to n minus 2, which is equal to 1 minus 1 upon n raised to n minus 2. And as you see, there is nothing special about j. If I choose different L, then it also, the probability that L will be a leaf is the same. Okay? The right way of handling this is to define a random variable. What kind of random variable? I define a random variable on the sample space that consists of all the trees, all the n raised to n minus 2 trees. So I have a sample space which consists of define a random variable one, if j is a leaf of t, 0 if j is not. These are called indicator random variables. Then equivalently what we are saying is expectation of this random variable, the mean of this random variable is given by this. You expect it to be a leaf with that kind of probability. This kind of setup is useful in many discrete situations. This is what is done. For example, if I catch hold of a permutation, a random permutation, how many fixed points does it have? How do I handle this? Whether this fellow is a fixed point, that fellow is a fixed point, and then I add up all the fixed points. So what is, we just have to see what is it that x counts. X counts number of leaves in the tree. X of t is just the number of leaves in the tree. X of t is literally counts how many leaves your tree has. If your tree has 4 leaves, then x of t will be equal to 4. Okay? Very fortunately, the main result in the theory, in probability theory we need to use is, unlike other things, expectations add. Expectations add up. It doesn't require these to be even independent or anything like that. That's irrelevant. the expectations of random variables can be added, and their expectations also add. What does that mean? Expectation of x is the sum of expectations of these. This is fixed now, n is fixed, so each summand is fixed, so I'll get n times this. Little manipulation should be helpful here. N multiplied by 1 minus 1 upon n raised to n multiplied by 1 minus 1 upon n raised to minus 2. Fortunately, now just question of interpretation. Of course, I should have done this before. The slight, just look at expectation of xj. This is 1 minus 1 upon n raised to n multiplied by 1 minus 1 upon n raised to minus 2. Okay? What is not clear? If you now take the limit of this as n goes to infinity, this term will get suppressed, that's irrelevant. As n goes to infinity, this goes to 1. There's no problem at all. Okay, this is just a 1 divided by quadratic kind of expression. So this goes to 1 as n goes to infinity. What about this as n goes to infinity? This is e raised to minus 1. It goes to e raised to minus 1. So expectation of xj is 1 upon e as n goes to infinity, as the number becomes large. And what that means is expectation of x what does this tell us? This is a quite surprising result. What that means is, do you know roughly 1 upon e is, how big is 1 upon e? This is approximately 0.37. Okay? 1 upon e is roughly of that order, 0.37. What that means is, if I take a random tree on 100 vertices, then about 37 vertices will be leaves, which is actually quite a large number. Actually, it's quite a large number. So randomly chosen tree should be expected to have quite a large number of leaves and not a small number of leaves. The probability that a randomly chosen tree on 100 vertices will have very few, like 6 or 8 or 10 leaves, is very, very small. It should be expected to have about 37 leaves. If you have a randomly chosen tree on 1000 vertices, it will have as many as 370 leaves. So number of leaves actually is very significant. Is it clear? A result with which, without this computation, without proof of code and all this, would have been very difficult to imagine. It would have been very difficult to see that this is the case. Okay? When 0.37 actually is quite large number. It's bigger than 1/3. So an average tree on n vertices has more than its vertices, more than 1/3 of its vertices are leaves. So middle vertices are not too many, there are just about 2/3 of them. Okay, so you get a rough idea. So that was a slight detour into probability. Now we become more ambitious, more general. This is fine. We know that number of spanning trees in complete graph is n raised to n minus 2. Thanks to whatever I had written earlier. The total number of spanning trees for complete graph is n power n minus 2. This question can be asked in general. I give you a graph and you want to tell me the number of spanning trees in that graph. The job is easy in case you can spot that the graph is not connected. If the graph is not connected, there is no question of having a spanning tree. The number of spanning trees is 0. But if the graph is connected, counting the number of spanning trees in a given graph is a non-trivial task. It's quite a non-trivial task. Okay? So definition, number of spanning trees. For example, if you take a cycle on 10 vertices, how is that obvious? Because I can drop any edge. If you just remove any edge, the resulting thing will become a path. And this is the only way you can construct a spanning tree. This is like, because you have to break cycles. There is a cycle, you can break it by deleting any edge, and there are 10 ways in which you can delete the edge, therefore it's equal to 10. Or in general, tau of Cn is equal to n. But this question could be pretty complicated in case your graph is not all that easy to look at. For example, how many spanning trees does Peterson graph have? How many spanning trees does the cube graph have? Even the simplest thing like the cube graph, the three-dimensional cube, which has only 8 vertices, has as many as 384 spanning trees. Therefore, counting these things purely by hand way would be very difficult. You need some theory. At the same time, it's an important question. It is quite an important question. Therefore, you need some machinery. One way of handling this, and this is what is done. So, let me define this. Definition. Contraction is the graph obtained by identifying x with y or y with x. Okay, so let's see an example. Now those two vertices have merged into a single vertex. Is it clear? X and y have become only one vertex. That edge will be removed. This vertex, if I call this Z, so this vertex is actually, it's like a fat vertex which you can call xy. And that vertex called Z is now was adjacent to x, it was also adjacent to y. Therefore you make it doubly adjacent. Okay, so this can result, the bad part here is it can result in a multigraph. This can, as it does there, it can result in a multigraph. When you contract an edge, so the number of edges in the contraction will be one less than the number of edges in G. Number of vertices will also be one less than the number of edges in G. Here is the theorem. Okay, I'll leave the proof of this to you. How is any spanning tree in G constructed? A spanning tree in G is constructed either that spanning tree uses E or it does not use E. If it does not use E at all, then it is the number of spanning trees in G minus E. And just see how G minus E will look like here. Anything which is a spanning tree in this will also become a spanning tree in that, clearly. Okay? Plus those spanning trees which must use that edge. Any spanning tree which uses that edge actually corresponds to, there is a one-to-one correspondence between these. Okay? This is something I am leaving to you to work out. Okay? Just see why for every spanning tree here, you get a spanning tree here which uses E, which does use E. Okay? These are two distinct cases. Either your spanning tree uses E or does not use E. If it does not use E, then easy. Then you are in that situation. If it uses E, then you can build up corresponding thing there. Okay? And this is a typical example of a recursion, statement in recursion. What one can do is sequentially go on deleting edges that way. So to find the number of spanning trees here, I choose another edge in this, and so I apply this formula recursively. Unfortunately, it is not as easy as it appears to be. If your graph has as many as 100 edges, then you will have to apply this 100 times. Okay, and it will be quite messy. So in terms of algorithmic complexity, this is not a very powerful procedure. This is not a very effective procedure. It's a good theorem, but not computationally very useful. It's not computationally useful. It's good to know that some such thing exists, but in actuality, it's not going to be used when it comes to computing things. In order to handle things in general, there is a general enough theory that one has to develop. I'll begin discussing it today, and in the next class we should be able to finish it off. What you have now is G is a given graph. Fixed. In fact, you can assume that it's a simple graph. What we want to do is associate two vector spaces with G. There are two vector spaces I am going to associate with G. These vector spaces are vector spaces of functions on the set of edges of G. So what is the rough idea of what is going to come? We are going to construct functions to the field of real numbers, let's say. So let's assume that you have n vertices, m edges. So this is a function whose domain has m elements and is a real valued function. In order to do that, what we'll also do is G is a given graph. As I said, there are no directions on the edges. No directions on the edges. For the theory that we want to develop, we'll put arbitrary directions on the edges of G. Is that clear? This is a surprising thing. So what I'm going to do is, I'll put directions on the edges in any manner I want to. So, in some sense, we're making life more complicated. Is it clear? We're making life complicated. But a nice part of this entire thing is that the final outcome will not depend on the manner in which you put these directions. So make G directed by putting main thing is in any manner. Let's see what do I mean by that. Let's take a graph. In fact, if the number of edges is m, there could be 2 raised to m ways of doing this. There will be. We now make an incidence matrix of this directed graph. How do we make this incidence matrix? X is the vertex, E is an edge. Really speaking, I will not specify what that. So it's going out of X. Is that clear? I don't care what that other vertex is. Irrelevant. For example, that graph is big. Let me take a smaller graph just to give you an idea of how the incidence matrix. Okay. Even is the edge going from x1 to x4. So the rows are indexed by vertices. columns by edges, E1, E2, E3, E4, E5. E1 is going from x1 to x4, therefore I put a plus 1 here, I put a minus 1 here, put zeros there. Is that clear? Next, E2 goes from x2 to x1, therefore you put a plus 1 there, minus 1 there, put zeros everywhere else. E3 goes from x3 to x2, therefore you put a plus 1 here, minus 1 here, zeros everywhere else. E4 goes from x4 to x3, so you put a plus 1 here, minus 1 here, zeros. E5 goes from x2 to x4. So this is incidence matrix. This will of course change if I change the directions. Is that clear? I'm not saying if I reverse those directions, that matrix will of course change. The plus 1, minus 1s will change. They will. But I'll assume that I put these directions once for all, and then we develop the entire theory. And then, in a very surprising manner, the entire theory that we develop, we see that all the theorems that we prove, they would not depend on the directions that we put. Is that clear? So they will be direction free. They will be free of these directions. Therefore it does not matter, is what we are going to come out with. It's not obvious. It's something that's not completely obvious, but it's true. Look at the way this construction is taking place. In every column, there is exactly 1 plus 1, 1 minus 1. The remaining entries are all equal to 0. Therefore, in each column, the sum will be equal to 0. Therefore, all the rows of this matrix, they add to 0, 0, 0. So if you look at these, there are two ways of looking at this. There are 4 row vectors here. There are 4 row vectors. These row vectors add to a 0 row vector. Okay, 0, 0, 0, 0, 0. Okay, so these, in fact, I can say something immediately. If somebody asks me to calculate the rank of this matrix, it is not equal to 4 for sure, because rows are linearly dependent. And this is quite true. This is true for all incidence matrices. Incidence matrix is an n by m matrix in which the rows are linearly dependent. Rows are actually linearly dependent. Definition. F is called a circulation. Okay, I have to explain what this means. F plus x means, look at what I'm going to do is, there will be edges at x that are going out. There will be some edges at x that are coming in. So this is for the going out thing. That is coming in. Where E has the form x out. Anything that is coming into x. For example, in this picture, there are 2 edges coming into x and 3 edges going out of x. Suppose just to get an idea of circulation, suppose this is 7, this is 2, this is 4. 7 plus 2 is 9 plus 4 is 13. And suppose this was 11 and this was 2. Then there is a balance here. Is that clear? Whatever is going out, equal quantity is coming in. That is what. And this must happen locally at every vertex. At every vertex, this balance must hold. It is not essential that we write only positive numbers, not necessarily. It could be numbers like 7, minus 3, minus 4. This is fine. Is it clear? The net sum of what is going out is 0 here. Net sum of what is coming in is also 0. Is that clear? Therefore that equation is satisfied. What I have showed you is only at one vertex x. This must hold at every vertex x. Such a thing is to be called a circulation. Circulations exist. Circulations exist in any graph because, for obvious reasons, this manipulation can of course be worked out, but there is a zero circulation. I can just decide to the zero function is a zero circulation. Maybe there are situations where zero circulation is the only circulation possible. Think of which graphs will have only zero circulation as the circulation. You can think about it when you go home. Circulations can be added. Sorry? Star. Yeah. For a tree, for example, how can you have a balance at a leaf? At a leaf you cannot have a balance except by writing a 0. Okay? And then you think about it. Sequentially you should be able to construct things that way. Okay? So think about it. I can add circulations. Circulation is a function on the H set. If F is a circulation, G is a circulation, then F plus G is a circulation. How is that defined? And if F happens to be a circulation, G happens to be a circulation, then F plus G, that balance will be satisfied for F plus G also. That equation will hold for F plus G. Therefore, sum of circulations is a circulation. If lambda is a scalar, what that means is set of all circulations is a vector space. It is a vector space. Set of all circulations, these two things tell us that set of all circulations is a vector space. The cycle space. What matters for us is the dimension of this cycle space, etc. So these are the linear algebraic parameters that we are going to look at. There are interesting circulations that one can always work out. Let me give you an idea. Take a cycle. For example, suppose your graph has a cycle. Draw slightly long. Is it clear that if my graph has a cycle, all the edges don't have to be oriented in the same direction? Because we already said that you have freedom to put directions. Therefore, you cannot demand really that they're all going that way. Not necessarily. You cannot take that freedom. What I want to do is, based on this cycle, I want to define a circulation. What is it that I do then? I put a direction. This is the anti-clockwise direction, counterclockwise direction. Some of these edges agree with this direction, some of them disagree with this direction. For example, x1, x2 agrees, but x2, x3 does not agree. It is actually opposite to that direction. What I am going to do is, if your edge agrees with this direction, write a +1. So this is a function I am going to define. Write a +1 because it agrees. Write a -1 in case if it disagrees. Write a +1 here. Write a +1 here again. Write opposite, therefore write a -1. Agrees, therefore write a +1. What do I do with other edges? This is only part of that graph. This is not the whole graph. There are other edges there. What do I do with these other edges irrespective of whatever direction? I just put a 0. Does not matter. Okay, so I focus only on this cycle. My claim is this is a circulation. This is a circulation. How do I know that? At every vertex on any vertex which is not on that cycle, like this vertex here, that equation is clearly satisfied. There is nothing to check. 0 is coming in, 0 is going out, absolutely no problems. It is only the vertices on the cycle which I need to bother about. Look at a vertex on the cycle. There are only 2 edges. There may be hundreds of other edges at that, but their contribution, no matter whether it's going out or in, that is 0. Therefore, that need not be looked at all. It is only 2 edges that bother us. At the phenomenon with those 2 edges, there are 4 possibilities. Let's see how this works out. It could be both are going out. If both are going out, my claim is one of these will agree with that anti-clockwise direction, other one will disagree necessarily. It has to be that way. If both are going out, it cannot be true that both of them agree with that anti-clockwise direction. Intuition. Now there's nothing more one can do to explain this point. Therefore, on one you will be writing a +1, on the other you will be writing a -1. Therefore, net outflow is 0. There is nothing that is coming in, of course, at this vertex. No problems. Therefore, at this vertex that balance is met. It is possible that both are coming in. I would exactly argue the same way. One of them will agree with that anti-clockwise direction, one will disagree. So in one case I'll be writing a +1, other case I'll be writing a -1. So the net thing coming in is 0. Nothing is going out anyway. Therefore that balance is maintained. It is possible that now both are agreeing. Let's say both are agreeing the direction. Then you will be writing a +1 here. You will also be writing a +1 here. What that means is one is going out, but one is also coming in. Therefore, there is balance here. Okay? It may be you are going in the other direction. It could be something like this. Then -1 is coming in, -1 is also going out. Therefore, in all 4 possibilities, you're done. Therefore, this is a circulation. Therefore, whenever you have a cycle in the graph, you can construct a non-zero circulation. You can construct a non-zero circulation. It so happens that the vector space of all circulations, the cycle space, is generated by these kinds of circulations. These are called the fundamental circulations associated with the graph. Is that clear? Along with this, I want to define another vector space. I want to define another vector space. This, incidentally, the vector space C is a space of functions. Where are these functions from? These are functions from the set of all. There are as many as m edges. Therefore, it's a subspace of R power m. I will define another vector space. In order to define that, we need a different idea. Instead of putting a function on the edges, I'll put a function on the vertices. I'll make functions on vertices. Vertex set. This is what is called potential. And which is why this is called potential difference. That's exactly like voltage. For example, just put numbers 3, 0. What would I be writing here? It's 3 minus 0, therefore it's 3. It's minus 4 minus 3, therefore it's minus 7. 6 minus 4. No, I think I'm 3. Okay, no, I think 0 minus 3, therefore this should be minus 3. 3 minus 4, therefore it should be 7. Minus 4 minus 6, therefore it's minus 10. 6 minus 0, therefore it should be 6. And 0 minus 4, therefore it should be minus 4. Okay, so that's the potential difference. The same potential difference can be obtained using different potentials. This is clear, because instead of, I could have shifted these numbers, I could linear shift. Instead of writing 3 here, I could write 4. I can add 1 to each one of these numbers, I'll get the same potential differences. Therefore, for what matters for our purpose is the potential differences, not the potential as such. I don't care about potential. It is the potential difference which matters for our purpose. Just as circulations can be added, potential differences now are functions on the edges. After all, our interest is in looking at functions on edges, not on vertices. Potential differences can be added very clearly. Potentials can be added, therefore potential differences can also be added. You can multiply a potential difference by a scalar to get another potential difference. Therefore, set of all potential differences form a vector space, which is what is called the bond space. One of the most fundamental statements in this theory is that these two vector spaces B and C, they are orthogonal complements of each other. They are actually orthogonal complements of each other. Therefore, knowing dimension of one tells you dimension of other. They are orthogonal complements. Okay, so this is the beauty of this RM. In case your graph is connected, then the potential difference, the vector, the bond space has dimension exactly equal to n minus 1. Its dimension is exactly equal to n minus 1. In fact, it's if and only if. And then based on this one can calculate the number of spanning trees, etc. So you see how large the model is. I mean, we require the model to be sufficiently abstract, sufficiently large in order to handle this far more general situation. Okay, something which couldn't have been handled just by the clever trickery of proof of code. Okay, proof of codes are good, etc., but they work only for complete graphs. They don't work for graphs in general. So we'll stop here for today.